Hey, and welcome everybody to Advent of Code 2022, Day 7. So, I'm eating my words from yesterday. It finally happened. The step change in difficulty seems to have seems to be upon us. Um, yeah, so this not a crazy difficult problem, but definitely more complicated than other problems we've had up to now, and definitely confused me a little bit at times, and I ended up making some silly mistakes. So when I approached this problem, I didn't have a great intuition initially as to how I should do it, and then I kind of ended up trying some things and then got confused in the middle there, and then I figured out that I had actually the perfectly fine approach to solve the problem, and I just stripped out a bunch of the random stuff that I had written and got it done. Got it done in the end. It took me a little bit longer than the ones up to now have taken, but yeah, it was a good problem all the same. So let's jump in then and talk about the problem. Day 7, no space left on device. So the elves, they've really hit you with this communication device that they gave you. Basically, you're wandering around and you realize that the communication system isn't the only thing that was broken on this device that they gave you. So you try to run a system update, and it says that there's no space left on the device. So what you start to do is you start to navigate around the file system, having a look at the sizes of all the files on it, which is your puzzle input. Basically, this is your puzzle input here. It's pretty much like the output of terminal commands, so CDing around to directories, listing what's in the directories, and yeah, that's pretty much it, going up and down your file system tree, and you've got the different sizes of all the files that are on it. What it wants you to do basically is to go through your file system, and it wants you to figure out all of the sizes of all of the directories on your system, and then with that it wants you to do some sort of information with it. It wants you to do some sort of calculation with it. So for the first part, what it asks you to do is figure out what is the sum total of the total size of the directories that have a size of less than 100,000. So it tells you that the total size of a directory is the sum of all of the files that are within it and all of the files of the subdirectories within it as well. So you can see here in the nice graphical presentation they have here, we've got the root directory, we've got A, and then we've got E underneath. So E is a directory. Inside it, it has a file I, which is the only thing that's inside that directory, and its size is 584, which means that the directory E's total size is 584. Then if we were to go up to the level A, the size of the directory A is the sum of all of the files that are in it, which is this G, F, and H.lst. So it's the sum of those, as well as the size of E. And we already figured out what the size of E was. It was this, which is the sum total of all the files inside it. So when you look at this, there's a couple of things that hopefully would jump to mind, a couple of things that jump to my mind to try and solve this. The first is trying to think of building the structure that you need to be able to represent this information in terms of like the data model. So for me, the data type I wanted to use to solve this was basically I wanted to create this file system tree in memory, and then I also needed to be able to do operations on it. And one of my favorite ways to do this is generally using recursion. So you'll build your tree, and then using recursion, you'll recursively walk that tree to then visit each of your nodes in the tree and maybe do something with them. Turns out in this case, that's not quite the way that you have to do it, but ultimately I think there is value in building your file system tree anyway, and then you have to sort of walk that tree. As it happens, the input in here, it contains not only the definition of what is the file system tree, but it also contains all of your commands in steps, basically, which effectively forms a recursion, because you're taking a step down, you're looking what's in there, and then you take a step back up. The step back up you could think of as the return portion of the recursion. So we're getting a little bit abstract here, but anyway, let's jump into some code and I'll talk through how I implemented my solution to this, and we can go from there. So, part 1. Let's run it. And it runs. There we go. Nice and fast. So, what are we doing for this? First of all, I start off defining my file system at the top. So my file system, in this case, I've decided that basically my tree is just going to be a hash. And with that hash, each key in the hash is going to be the identifier for either like a file or a directory. If it's a directory, then the value in that hash is another hash. If it's a file, the value in it is an integer, which is just the size of the file. So with these kind of nested hashes, we'll be able to effectively make a tree as you step down through it. So if you're in the root and then you have a file inside here, we know we will have some elements. Okay, cat. That was interesting. We'll have some elements in there, and the ones that are directories will be other hashes. So if you were to go into that one, then you'll see what's inside that directory, so on and so forth. For convenience, I've done a couple of things. Inside each of these directory hashes, we've got a convenience element that's just a name, and then we also have another thing which is the size, which is initialized to 0. Next thing I'm doing here is I'm creating a stack, which is just an array, but then using it as a stack would be because we'll do pop and push onto it only. This is a little bit abstract again, but basically, as we're stepping through this entire set of instructions, there are commands that bring us down the tree, and then there are also commands that bring us back up the tree. Going down the tree is fine because as we go down the tree, we're sort of creating what are the next files and directories. But as we go back up the tree, that's where things get a little trickier because you need to know what was the last one you were on. So for that, I'm using a stack so that when you go down one, we add something to that stack to tell us where we're going back to, so that then when we do the up command, we go up one, we can pop off the stack again so we know where we are then, so we don't lose track of where we are. This is something that was confusing me when I was doing my original implementation. I was using like a variable to hold like last parent type thing, and then I was also using a stack because in my head for some reason those weren't the same thing, and then I was confusing myself. Turned out, yeah, get rid of the variable and just keep with the stack ended up being the way to solve the problem for me. Okay, so now that we've talked about that, we're going to move on. Actually, the last thing. So the actual problem for the question wants you to be able to list out, say, the set of all the directories with all their sizes. So what I decided would be a useful thing to do was to have another dictionary, which is just a flat structure where the key is each directory name and the value will be the total size in it. So as we loop through the entire data structure, we can just insert those. So at the end, we have a flat list of all the directories and their sizes that we can do operations on. And it's that flat list at the end that actually ends up being what we use to compute our solution. So now getting into the meat of it is actually building the tree structure and assembling this directories data structure here. So what we're doing here is reading every single line from the file. And so for each line, we're just doing a split operation on it to separate out all the parts of it. The structure is fairly simple. We're told that all of the commands start with a $sign, which makes them easy to parse out from the other things. You'll notice that if it starts with a $sign and then, so if we split this into an array, we'll always have 3 for these commands, 2 for these, and then 2 for everything else. So the first index will always be, if it's a $sign, we know it's a command. So then what we need to determine is whether it's a CD command or an ls command. It turns out, the way I've implemented it, the ls commands actually don't do anything in the system. So the first thing I've said here is that if it's an ls command, we'll just skip, move on to the next thing because we don't actually care. So we know it's not an ls command. We know it's a command, which means it has to be a cd command, which brings us to a new directory or the previous directory. So for the first part, we're going to do it. We'll check if it's an up directory move. So for an up directory move, I'll explain this thing in a second, but ultimately what you're actually interested in is you're interested in just popping off the stack to figure out to get to the previous directory. So we want to move up one, so we'll just pop off the stack to move up. The rest of this stuff I will explain in a minute. So then if it's not an cd up command, it's a cd to the next into a new directory command. So in that case, we want to take our stack and we want to push onto that stack some new directory. So in this case, what we have is we have on the last index, cat, get down off those curtains. Sorry, the cat is going wild here for my curtains. So I'm going to have to put you out maybe. You want to go out? Go on. Go ahead. I should make up her own mind in a minute. Anyway. So yeah, we know that we have a list of what the elements are. So you can't cd into a directory unless you know what's in that directory. So the stack already contains that. So we're able to say, take the last element from the stack, which is where we currently are basically, and then the input, which is this index here, is effectively the input that we're cding into. It's saying cd into directory A, directory D. We push that onto the stack, and it is cold, and then that'll do it. So that's our cding around. Now the only thing that's left is parsing the output of the ls command, which is effectively all of these guys. So I said that the ls command doesn't do anything in my solution. It doesn't, but what is its output that gets written to the screen is what we're actually processing. So we skip on these ls commands, but we do stuff for the rest of these. So when it's listing out files and directories, we're going to do some operations to these. Excuse me. So what do we do? In our case here, we have our stack. We have our last thing that's on the stack. We know that the last thing on the stack is basically our current directory. So inside the current directory, we're going to push, if it's a directory, we're going to push into there a new hash, which is what I said earlier. And this time it's going to be empty. It has its name put into it and it has a size of 0. And if it's not a directory, we're just going to push in the value from the file. So effectively, we push in this thing if it's a directory that we've read. So if the if the first character is dir, we do that. We just push in the title, an empty thing. And if it's a file, we know the number is just the first thing for it, and that's it. So with that in mind, that's it's a little bit convoluted, but effectively what doing this does is it builds up your hash to be a tree, and it builds up the entire file system in memory. So what I was thinking, the next thing I had to do was I was contemplating the idea that, well, maybe now I need to, once I have that tree structure built, then I'm going to have to walk the tree. And that's where I was thinking, well, now do I need to write a recursive algorithm that'll walk the tree and figure out all the values? That's when I realized that because of the way the commands are structured, you're already doing a recursion. You're already doing a walk by processing the input file and moving each step down. You're already walking the tree anyway, so you can just do all your operations here as you're building the tree. So I decided that I would do all my computations here. So the way that works is, effectively, you have to think about what you're doing when you're doing a recursion. You extract your cumulative value of a recursion when you return from it. So if you're doing a cumulative sum, when you return, that's where you're extracting the values of each thing and you add them all together. So in this case, with these walking down the tree, the analogy to where that happens is when you do your cd ... command. So that's what all this mess here is for. This mess in here is to calculate the size of the current directory that you're in when you leave it. So when you go up out of the directory, that's when you want to calculate the size. So the way this works, if you're thing, if there's just files inside your bottom level directory, then you just sum all their values together, which is simply down here. We'll do a loop, go through every single thing that's in this. I'm skipping the size and name keys because we know size and name are ones we've set up. Every other key in here should be either a directory or a file. So we loop through that, then we sum together if it's just a value, then if it's just an integer value, so we check if it's a hash or not. If it's not a hash, it means it's just an integer, so we'll just sum that together. If it is a hash, that means it's a directory that we're looking at. But conveniently, directories have this handy little size property that I added to them. So we'll return that size property. So we still just do a cumulative sum. But now you might ask, well, how do you calculate? How do I set that size? How do I know that my sizes are actually going to be there? Because once you get to the bottom of this, you know that everything that's in here just has to be files. It can't be directories. Because if it was a directory, you would have CD'd into it. Now, that's a bit of an assumption to make, but what we're assuming is that in our input file, every time there's a file, we actually CD into it. And if there's a folder, we CD into it. But there might not be, so I initialize them all to 0 because we don't necessarily need to CD into it. And if we don't CD into it, we're assuming it's empty, so we assume that it's 0. So that's a bit of an assumption, but it does appear to work, so that's fine. We move on. So we computed our sizes. We stick our size back into the folder structure. We go back up into the next directory, and we effectively do the same thing again each time we go up and up. So yeah, that makes sense. Now, I should talk about a little hack I had to do. So I actually had to add some stuff to my input. So my input, the inputs don't end at the root directory, and also they don't have to end at the root directory. So you'll see in the example, the last thing, if I go to the sample, the last thing we do here is we CD into directory D and we do an ls to list out all its files. We don't then CD back up one. So that means that if I was to apply this algorithm, which I did, this file size, folder size for D wouldn't actually end up being computed because it would never end up going, it wouldn't do the backup step. So what I did was I just added one single CD ... to the end of this and it worked. But for my actual input, I was thinking, well, how do I know? And the thing is, you have no idea how far into the tree you're actually going to be when you reach the end of your file, but you still need to get back up to the top. So what I did was I ran it once and then I checked the height of the stack, and the height of the stack was still, like, I think it was at 3. So then in my input file, I just added 3 CD ... to the end of the input file to get me back up to the root directory. And that meant that I computed everything back up to the root directory properly. What else is in here then? Yeah, so then the last thing that you need to do to be able to solve the problem is you need to be able to insert the size of that directory that you've just computed its size. You need to insert that into our flat list of all the directories. So that's what this part down here does is, so we've set our size, we know what that is, we've calculated it by the sum of all of its contents. Now we need to insert it into this. So this gets a bit confusing again. Basically, the crux of this part, why I did this, was because files aren't globally unique, or directories aren't globally unique. So somewhere in the tree, there can be 2 directories with the same name. They're unique in context, but they're not actually globally unique names. So if you just take the name of them, you actually will lose some of your data here. So you need to figure out a way of making them globally unique. I didn't figure out a way of making them globally unique, so this technically isn't a complete solution. It may not work for you, but what I did was I set, well, what's the parent directory that I'm in, and I appended that onto the name, and that gave me enough uniqueness to get the full amount of all the directories. I don't know if that's a generic thing, that there's never a depth more than 2 where there's a file name the same. There might be in some inputs, I don't know. But for mine, there wasn't, so this worked. But yeah, you could do it any other way. The actual directories don't matter here. So you could just come up with you could just index these, it wouldn't matter. And it's fine. Or you could just use an array. I use the dictionary but you could actually just use an array for this. It's fine. This just got me around the problem that I was experiencing because I was missing data. I was losing, my values weren't right when I summed them at the end. So yeah, okay. As I've talked through that, I've realized that my solution may actually be somewhat convoluted. But anyway, this is the way I thought to do it. So to get to, what did I do there? To get to the actual final bits of the solution, then once I had my value, all of my directories with their values, all you do is do a select where you're finding all of the values that are less than 100,000, sum them all together, that gives you your answer. And then the second part is essentially similar kind of thing. So for the second part, what they want you to do is they want you to figure out what the file sizes are. So you have the update file, you know what the update file size, you know the total system size. So basically you're trying to find the folder that you should delete to give you just enough space to install the update file. In that case, they tell you that this is 70 million is the size of your system. They tell you the update file is 30 million. You figure out the total file system size, which is effectively your root directory, what the size of your root directory is. You then take that away from this total, and then you take that away from the size of the input. That gives you an amount of space needed. Then you basically go through all of your directories, find every file that's bigger than the space needed, and take the smallest one, because that's what they tell you to do, and that gives you your answer. So if I do part 2 runs, and we're done. It runs a little bit slower than the other one, but it's much the same. Most of the bulk of it is in building the file system. There's other ways to do this. I'm sure. I hope there's simpler ways to do this. I might have overcomplicated this, but yeah, this is the way I did it. So this has been an extremely long walkthrough, way longer than I wanted these videos to be. I'm going to try and condense this down, but I felt like this is a complicated one to explain. So hopefully you guys learned something. Hopefully this made sense, and I'll see you all tomorrow for what is hopefully not as difficult a problem. Bye bye.